35. All right, we're going to talk about the second part of finding limits analytically. Morning. So we're going to be able to answer the question by the end, why do functions that agree in all but one point make a difference with the limits? Did I hit the button? I can't remember. Yes, I did. Okay. All right. So let's go ahead and talk about this right here. So let's try what we did last week. Let's go ahead, and we decided last week that we could substitute something in, right? So if I started by direct substitution, I would put in 1, what's 1 cubed? 1 minus 1 over, what do we get for, what happens here? Probably not a great example because the numerator comes out there, but this is a big problem, isn't it? I can't have the denominator come out 0. All right, so I have to have a way to deal with that. So what's really going on here is that's the picture of the function, okay? It's a parabola, but it has a hole right here. We've learned last week, because we talked about limits graphically, that it does have a limit because it's right and its left-hand side match. Okay, so there is a limit. However, it just doesn't have a value at that point, so we can't just plug in. So we have to adjust it a little bit. Okay, so that's what it looks like if the hole is plugged in. It's a function that is off by all, it's the same in all except 1 point, okay? So we have this theorem. I don't know if there's anything for you to fill in. Is there stuff for you to fill in? No. Okay, you didn't even have the, oh, you guess you do have the graphs in example 1 there. So C is a real number. We're going to let f and g equal each other. So the two functions in all except for one place, C, okay, on an open interval containing C. If the limit of g approaches c exists, then the limit of f also exists. So as long as our original or our original function g exists a limit, this one also exists a limit at that point. As long as the only difference is there's a hole in the graph. Okay, that's what that's saying. So let's try this. So I need to do what I'm going to do in order to find that limit is I'm going to factor. So I'm going to factor, haven't taken the limit yet, so I still have to write this. The limit as x approaches 1. All right, what kind of factoring is the numerator? It's not a trinomial. It's a cube, good. All right. What is the cubed root of x cubed? X, what's the cubed root of 1? 1. Okay, oh, I forgot to put in my signs. What are my signs? Minus, plus, plus. All right, how do I, or what do I do now with the x?
You square the x minus 1.
Square it, and what do I do with the 1? Square it, and then we ignore the sign and multiply together for the middle, so I just get x. So what happens with the x minus 1 and the x minus 1? They cancel. Now if I sub in, am I going to get a 0 in the denominator? No, I won't. Okay, and now I'll actually be able to get to the limit that we can see on the graph there. So notice, I have yet to take the limit. I still write the limit out in front. Once I substitute in, that's when I get rid of the limit notation out front, because now we're finally evaluating. So I'm plugging in the 1. What's 1 squared? 1. Plus 1 plus 1. What's 1 plus 1 plus 1? 3. Check the graph out. You guys had the graph there, right? Is that correct? Is it approaching 3? Yep, from both sides, so we're good. So the big key today is, if it doesn't work, factor first. Okay, if you get a 0 in the denominator, factor first. All right, so our instructions have switched to find the limit of the function if it exists. Write a simpler function that agrees with the given function in all but one point. If we need to, we could use the calculator to confirm our results. I told you guys you can check the old graphing calculators out of the library, right? There's also an app on Google, I think it is. It's called Desmos. That is a graphing calculator. I played with it a little bit this summer. I don't know if it's an app or if it's just a website, but if you search that, I'm sure you'll find it. But I know it'll at least graph for you. Okay, I don't know what else it will do, but I know it'll at least graph for you. If you type in free graphing calculator, I'm sure you'll find one. If you have a Mac, I think there's one built in. So you at least have access to something at home. All right, so we're going to do some good old factoring. I'm going to still write the limit as x approaches 2. Okay, so I'm not going to show you what to do. I want you to factor the top. So everybody factor it, and you're going to tell me what the answer is. Do we agree with Justice? Sure? We weren't confident? But what? No, go ahead and give him the point. You can do that on all of them like that or like that, because it would have simplified to the same thing. All right, so now what happens? They cancel, and technically when they cancel like that, what do we know about it in the graph? What does it look like in the graph when it cancels? It's a hole, okay? So we really have the limit as x approaches 2 of x plus 3. What am I going to do now? Plug in the 2. So we get 2 plus 3, which is 5. So we added one tiny little tweak to this today. It really didn't make it that much worse. Okay? So let's try it again. So how am I going to factor the numerator now? Difference of squares. So all that ugly factoring from last year is coming back. We don't tend to see grouping. We see cubes once in a while. Okay, it's a lot of quadratic factoring. All right, so what do we get with the cube or the square factoring? Okay, does it matter which order I do that in? Nope. Okay, so what do we get? What happens? X plus 2 is canceled, so I'm left with the limit as x approaches -2 of x minus 2. I'm writing a lot of steps, okay? I know some of you are going to be able to shortcut a little bit more, but you aren't just plugging in your head. I need to at least see you cancel, okay? All right, so what am I going to do now? Plug in the -2. What do we end up with? -4. All right, hopefully not so bad. We need, let's see, how many more do we have? Oh, a few. Okay. Let's do, why don't you try 4 and 5 on your own? They're a little bit harder, not much though. Still same concept. So everybody's doing 4 and 5 on their own before we get to 6, which looks kind of ugly. And it all jammed up. I'll give you about another 20-30 seconds to finish both 4 and 5. Okay, let's check it. What do you notice about 4? What's different about it? Good job. You have to factor both the top and the bottom, right? All right, good. I like the numerator and denominator vocabulary. That was good. I cheat sometimes. All right, what did you get the numerator to factor into? Do we agree? Minus and minus, right? Okay, let me fix it. All right, and then what's your denominator? X plus 2, x minus 2. All right, what cancels? That was the problem that was being caused. There's our nice little hole. So we have the limit as x approaches 2 of x minus 1 over x plus 2. All right, what do I do now? Plug in the numbers. So what are we going to get? We have 2 minus 1 over 2 plus 2. What's 2 minus 1? 1, and we're not freaked out by a fraction, right? We're in calculus now. Fraction shouldn't freak us out. Okay. Especially when it's the last part of the answer. We like them there. Okay. 5. What factor's here? Just the denominator, right? So we've got the limit as x approaches 1. X minus 1, what's the denominator factor into? X plus 1, x minus 1. The x minus 1's cancel. What's technically left in the numerator? There's a 1 hanging out in front always, so the numerator should still have a 1. If you dropped the 1 and you just brought the x plus 1 upstairs, you did it wrong. Okay, so you need to fix that in your notes. What do I need to do with this 1? Substitute it in. So 1 over 1 plus 1, which is 1 over what? 2. So hopefully not so bad so far. Okay. And then there's example 6. Looks like fun, doesn't it? All right, so here's the deal with example 6. When our entire lives, we've seen a radical in the denominator, and we've done what's called rationalizing the denominator, right? Well, the way this one is set up, I can't just plug a 0 in there. It would make it, we can't divide by 0. So what I have to do is I have to introduce something to the bottom that's not going to make it 0. So I'm going to rationalize the numerator, okay, which means I'm going to multiply top and bottom by the conjugate of the numerator. Okay, I know, I just threw you all off. So let's one step at a time. What's the conjugate of the numerator? Square root of x plus 1. That's the sign that needs to be changed, right? Plus 1. This first part is the first term. And same thing on the top and the bottom, so it's like multiplying by 1. All right, there's good news on the top. I still have to write this guy, limit as x approaches 0. It was a conjugate, so do I need all of this? No, what do I need? First and last only. Okay, so what's the square root of x plus 1 times the square root of x plus 1? X plus 1, whatever's underneath the radical. What's negative 1 times 1? Negative 1, good. In the denominator, I'm not going to distribute, I'm just going to leave it. X times the square root of x plus 1 plus 1. Our goal, though, is we got to get rid of that x, okay, because that's what's causing us problems right now. What happens here? They cancel. So now I'm down to the limit as x approaches 0 of x over x times square root of x plus 1 plus 1. And do you see the radical thing that I was talking about? That one is inside the radical. This one's outside. You got to be careful. Okay? Sometimes, see, I put the little tail on it. I'll put a little tail on it to let you know I'm done with that radical. Everything else beyond it is outside the radical. Okay, what happens now? The x is canceled. What's technically left in the numerator? A 1. So we've got the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now is it okay to sub in? So all we did was we played a trick on it, right? We figured out a way to get rid of the x in the denominator and not really manipulate the problem so it was a different problem that I could plug into. But we didn't change it in any way because we multiplied top and bottom by 1. Secret is to rationalize the numerator, okay? So I'm now plugging in. I can drop my limit out front. I've got 1 over the square root of 0 plus 1 plus 1. So let's see. What's 0 plus 1? What's square root of 1? So we have 1 plus 1, which is what? 2. So 1/2. I really should have had little equal signs. I sometimes will lose my equal signs. Okay. It's not a day unless we do trig, right? So there are some very special limits. Do you have to write those down, or are they already in there for you? There are. Gosh, I was too nice in these notes. All right, so these two are memorized things. You just have to memorize them. They work both directions as well, okay? So whenever you see sine x over x when the limit's approaching 0, we know that it's 1, okay? Just memorize it. This one is used all the time. Guarantee you're going to see it on the AP test. This one here, it's used sometimes. You need to know it. It'll probably be on your Chapter 1 test, okay, somewhere, because I want to make sure you've memorized it. But it may or may not come up on AP, all right? So the limit as x approaches 0 of 1 minus cosine x over x equals 0. This one here especially, it doesn't matter if the x is on the top or the bottom. It still equals 1. Okay, so as long as you have this relationship of sine x over x or x over sine x, then that limit is equal to 1. Okay? Doesn't matter which way it goes. All right, so we got to create that. So I'm going to rearrange this a little bit to try to isolate the sine x over x part. So I'm going to rewrite it as the limit as x approaches 0 of 1/3 times sine x over x. What did I do? Yeah, there's a 1 there, right? And I split the 1/3 off, and I split the sine x over x off. All right, what do we know that limit goes to? What did we just learn?
0.
Doesn't go to 0. It goes to 1. Okay, so make sure you just straighten out. The sine goes to 1, the cosine goes to 0. Okay, so think about it, right? If we were going to draw the sine graph, right, doesn't it start, isn't it? No, it doesn't. Never mind. Don't think about it. I'm wrong on that thinking. Okay, so it goes to 1. And let's see, what's 1/3 times 1? There's nothing else to plug into, right? We got rid of it, so it's 1/3. Okay, let's take a look at example 8. All right, can't sub in the, I don't have sine x over x, right? But I could try to create it, all right? So I'm going to rewrite it a little bit. I've got the limit as x approaches 0. I'm going to leave the 1 over x off to the right side. What's another name for tangent? There you go, sine x over cosine x. Could I rearrange that again? So I've got the limit as x approaches 0 of, I'm going to bring it 1 over cosine x times sine x over x. All I did was swap my numerators, which I can do because it's multiplication. What does this limit go to? 1. So I really have 1 over cosine of 0. Okay, cosine of 0 is there. What's the cosine of 0? 1. So I have 1 over 1, or just 1. Everybody okay? Again, it's a memorized thing. Okay. This here has to match with whatever's here. Okay? So if I've got, let me go back to this screen. If I've got a sine of 2x, I have to have a 2x in the denominator. If I've got a 5x, I have to have a 5x in the denominator. Does that make sense? So that whatever number there has to match. So if we don't have that number, we have to create that number. So what number do I need to introduce to the denominator? A 4. Okay? Which means I have to multiply top and bottom by 4 over 4, because multiplying by 1 doesn't change my function in any way. So I've got the limit as x approaches 0. I'm going to split it up a little bit. I've got 4 times sine of 4x over 4x. So what does that limit approach? 1. Okay, and so what's left behind? 4. There are times when we have to artificially introduce something, okay, to get it to work out to what we need it to be. Okay, you just got to start thinking like a mathematician. Okay, We add stuff in without changing it. 1 is our favorite way to do that, right? Okay. Well, it's going to think about it. There's example 10. Okay, example 10, slightly different, right? I'm going to split it up. We've got the cosine thing going on finally. So the limit as x approaches 0, I'm going to split it off into 5 times 1 minus cosine x over x. What did we learn that limit goes to? 0. So I really have 5 times 0, which is, so likely when you see the one with cosine, your limit's going to end up being 0. Not all the time, but that's a likely possibility. Okay. Interesting. Okay. So let's split that one up. What's this saying we do to the sine? Okay, we could do sine squared times, it means we're pulling it apart. There's 3 sines, right? I'm going to write it a little bit differently than that. So I'm going to write it limit as, 0, as x approaches 0 of sine x over x. And then I know I have 2 more sines left. And I could leave it sine squared. That's fine. Okay, I'm going to choose to pull it apart, though. Okay, what do we know that limit approaches? 1. So I really have the limit as x approaches 0 of sine x times sine x. All right, sine x is 1, 0. So what is, or sine 0 is the 1, 0 point. So what is the sine of 0? 0. Times sine of 0 is 0 times 0, which is 0. Gotta love trig. The answer is always 0, 1, right? All right. I know we're really looking forward to this last problem. It's one of our favorites in the summer work, right? We've seen that before. We're working up to something that's in chapter 2, I promise, okay? So you're going to probably have to do one of these in the homework, which is why I'm giving you one in the notes, okay, to get you ready for it. So all this is a formula. We're going to follow the instructions of the formula, okay? It's a formula is just a set of instructions, okay? This is the function that we're talking about. What does it say we're going to plug into the function? What's the triangle stand for? It's a Greek letter. What's the Greek letter? It's delta. Delta. X plus delta x, okay? Notice I can't plug the 0 in, right? That's why we're having to do, so we're going to have to do something with it, okay? So eventually we have to factor, simplify something. All right, so I'm starting by plugging. I'm going to start with my limit as delta x approaches 0. All right, it says first thing I do is I take x plus delta x and I plug it into 3x plus 1. So I'm going to put my 3x plus 1 in, and then I'm going to plug in my x plus delta x. Okay. Then it says subtract the function and just plug in what this time? Just x. So aren't I just going to write it the way it looks? Yep. Okay. Let's do some algebra and see what happens when we simplify. So I'm going to distribute that 3 in. So we've got the limit as delta x approaches 0. What do we get when we distribute? Plus 3 delta x plus 1. What am I going to do with this? Distribute as well, so minus 3x minus 1 all over delta x. All right, now what?
The 3x cancels out, the 1's cancel out with 3 delta x.
So we've got the limit as delta x approaches 0 of 3 delta x over delta x. What do you know? What happens now? The delta x's cancel. What's left? 3. What's wrong? Yes. It's a limit problem. How do you do the limit problem without the limit? Huh? What if you'd plugged the 0 into here? What would it have done to the denominator? Okay, that's why I needed to do it that way. All right? I promise it's going to be, I'm setting you up for chapter 2. I promise. Okay? Robert's back here laughing because he knows what happens in chapter 2. All right, we should be up to assignment number, no, we're up to week 2. Oh, we're at 11, that's right. So 11, okay? All right, and we've got time. I'm going to come around and stamp homework, so get that, I'll give you a minute. You get that written down. You could go grab books and get started on this, okay? And then I'm going to come around and stamp. Remember, you get bonus 20 points if you've got last week's work done today, but you can still